Now we're going to use the first part to prove the second part of the fundamental theorem. If f is a continuous function on a particular interval, and capital F is the antiderivative of f, that's what we proved in the first part, then we can use this nice slick formula to calculate the integral between the points A and B. And it's just by taking that antiderivative and then plugging the boundary points in. Really, really simple. So part one told us that an antiderivative does exist. And so we know from things that we were doing, there are a lot of antiderivatives that have that constant c that could be added to account for vertical translations. So let's use what we learned before, the assumption that the antiderivative of f does exist, and we'll call it, in this case, let's call it g, capital G. Just want to make a distinction between the capital F that we have in the um, in the uh, in the definition here, or the theorem here. All right, so part one tells us that an antiderivative of f exists. So let's name one of them. Capital G of x. So if capital F is a derivative also, an antiderivative of f, then it's going to be the same as g of x, but with some possible constant that has been added, right? Okay, so let's calculate f of b minus f of a. I'm starting on the right-hand side, and I want to show that I'm going to end up with what's on the left-hand side, show that these are actually, in fact, equal. So f of b minus f of a, using the definition we just put together, is going to be g of b plus some c, and then minus g of a plus some constant c. These two constants are going to cancel each other out. So then we're just going to have g, oops, g of b minus g of a. I know it looks like we're just making a variable exchange, but what we're doing is we're going back to the definition that we had before in part one of the theorem. And so now what I'm going to do is I'm going to rewrite these in terms of that definition that I've got underlined. Hang on, let me pause for a second. A little bit more room there. Okay, so now translating to that definition, we're going to say, all right, I'm going between A and B, f of t dt minus A to A of f of t dt. Where am I getting the A and the B? They're coming from this number that I've plugged in. See, g of x, that gives us what the upper bound is. And so that's interesting because we said in the last video that when we're going between the same boundary number, that this is actually going to be 0. That's going to go away completely. So putting this all together, we've got capital F of b minus f of a equals the integral from a to b of f of t dt. And that's what we were trying to show. Now here's where it's going to make a difference to you, is in problems that we can calculate. So I've got 5 example problems that we can do. And this is going to be really mind-blowing because based on the stuff we were doing last week, this makes it seem so much simpler. We are going to calculate this by thinking about what the antiderivative is. What function we originally have had that when we took the derivative, we got cosine of x? Well, that would be sine of x. So the fundamental theorem tells us that if we look at the antiderivative and we evaluate it between the two boundary points, pi, 0 and pi, we can calculate this by taking the upper bound and plugging it into the function, then subtracting off the lower bound plugged into the function. So this is 0 minus 0. In this case, we're getting 0 overall. Why would that be? Well, if we think about what it is that we're doing here, what does the graph of cosine look like between 0 and pi? It looks like this, right? So I've got this area here, positive area above the x-axis, versus this area here, negative area below the x-axis. They're canceling each other out and we're getting 0 for that integral. All right, let's look at the second one. Again, we're asking ourselves what the antiderivative of secant x times tangent x is. We know that if we were looking at secant of x, its derivative would have been secant times tangent. So I'm going to say, all right, the antiderivative is secant of x, and I'm going to evaluate that between the boundary points, negative pi over 4 and 0. I take the upper bound and plug it into the function first, and then I subtract off the boundary point, the lower boundary point. So secant of 0, it's going to be 1 over the cosine of 0. That's just 1. And then secant of negative pi over 4, that would be, cosine is going to be square root 2 over 2. So if we take the reciprocal of that, we're going to get square root of 2. Looking at number 3, that one's a little bit more complicated, right? I'm going to rewrite this. 3/2. Actually, we said a minute ago when we were looking at the constant rule. First of all, using the summation, I can split this into two separate integrals. So I'll do that first. I'll split this up into two separate integrals. Okay. And then the constant rule says that I can bring any constant out into the front. I just want to maybe simplify this so I'm minimizing what I'm looking at. Oops, I need to put a dx here in both of these. Okay, and then this one will be, I want to bring the 4 out into the front. And this will be dx over x squared. Okay. The reverse power rule says that when I take an integral of something, I'm going to raise the power up by 1 and then divide by the new power. So this 3/2 is kind of just out on the front. I'm going to raise the power up by 1, so that would go up to 3/2. And then I would divide by the new power. And I'm going to evaluate it between the bounds of 1 and 4. So that's my first term. Repeating that idea, what if we think about this as dx times, or actually, sorry, x to the negative squared dx. Think of it that way. So I'm going to raise the power up by 1. That'll be x to the negative first power and divide by that new power. It's the opposite of when we're taking derivatives. And that's going to be evaluated between 1 and 4 also. Okay, let's simplify this. For the first term, these 3/2 are going to cancel each other, right? So we'll have x to the 3/2 evaluated between 1 and 4. For the second term, the negative and the negative will cancel. So we'll have a plus 4, and then we're taking 1 over x and evaluating it between 1 and 4. All right, plugging that stuff in. 4, our x to the 3/2. See, it's going to be 2 cubed 8, and then 1 to the 3/2 will be 1. So this is the first part. And then for the second part, I'm going to have 4 times 1/4 minus 4 times 1. And then putting that all together, we have 4 overall. 7 minus 3. Yeah. All right, let me grab our number 4 up here. Number 4 was the integral from 0 to 1 of dx over x plus 1. So as a reminder, another way to think about this, when you put the dx in the numerator of a fraction, what we really mean is maybe 1 over x plus 1, and then the dx is here. But sometimes to shorthand, we put it as the numerator. Remember that we had this definition that when we take the derivative of natural log of x, that we get 1 over x. So thinking of the antiderivative, this is going to be the natural log of x plus 1, and then we're going to evaluate it between 0 and 1. So we're looking at the natural log of 2 minus the natural log of 1. Again, I plug the upper bound in first, and then I plug the lower bound in second. So that is going to be the natural log of 2. And then what was our fifth one? Oh yeah, okay. And then for number 5, we're looking at the integral between 0 and 1, and we're doing dx over x squared plus 1. So this is one of those formulas that we also learned a while back. Remember that the derivative of tangent inverse, this is one of the inverse trig functions, is equal to 1 over x squared plus 1. So our antiderivative here is going to be a tangent inverse of x evaluated between 0 and 1. So we want to know what's the angle that has a tangent of 1, and then what's the angle that has a tangent of 0. So this first one is pi over 4, and then the second one is 0. So our overall answer is pi over 4. All right, thank you for watching, and I will see you in class.